In this video, we will finally see a characterization of planar graphs. So the question I ask you here is the Peterson graph planar? So as we know, if the number of edges is strictly bigger than 3n minus 6, then G is non-planar. So we have a sufficient condition, we have a test to see if a graph is non-planar. But as we know, for example, K33 does not meet this condition, and yet it's still non-planar. So this is not a both necessary and sufficient condition to be non-planar. We can think of it like, yeah, a test to be non-planar. But we don't have a test to be planar. The only test we have right now to be planar is rearrange the edges and see if you can make it planar. I mean, there's other stuff we could look at, right? Like how we proved K33 was non-planar. We can look and use Euler's identity and the number of edges on the boundary of every region to show some results. That could possibly work, but that's more of a technique rather than a characterization. So the Peterson graph, for example, let's see. In the Peterson graph, what m is equal to 15, n is equal to 10, and so what, 3n minus 6, that's 24, and here we have m is strictly less than 3n minus 6. Again, this doesn't mean that P is planar or not, it just means it didn't pass this test to be non-planar. So we have this question, is it planar or not? All right, in order to understand this characterization of planar graphs, what we're going to need are a few concepts. So one is the concept of a subdivision, when one graph is considered to be a subdivision of the other. So this is now a second meaning of the word subdivision. In one hand, we have the subdivision operation, which, remember, takes every edge of a graph and replaces it with a vertex of degree 2. So a subdivision is just a graph that's obtained by subdividing some number of edges. So for example, if I have something like, what do I want to do for subdivision? Oh, something like, yeah, I'll use the book example, something like this. Let's actually, sorry. Maybe I have a triangle. Maybe I have something like this. Maybe this is my graph H. Well, I claim it's a subdivision of this graph over here. Or sorry, rather that, maybe I should switch these. So, sorry, rather, let's say, sorry, this should meet the definition. I claim H is a subdivision of G here. So that means that I can obtain H by subdividing some number of edges. So let's see how I can do this. I'm going to do this in steps, but we don't necessarily have to. What I'm going to do, I'm going to take this upper triangle here in G, and I'm going to take that and turn it into this 1, 2, 3, 4, this 5 cycle up here. In order to do that, I mean, there's a couple ways, but what I'll do is I'm going to subdivide this edge twice. So I'm going to stick in a vertex here and a vertex here, each of degree 2, and that's going to make this look like, so there's 1, 2, 3, I still have this vertex here, 4, that's now adjacent to that one. All right, I still have this triangle here, and I still just have this one little pendant edge. All right, well, what else can I do? Well, I'm going to take this triangle. I need to get this 4 cycle here. I'm going to take this triangle, and I'm going to subdivide this edge. And then I'm going to take this pendant edge, and I'm going to subdivide it twice. I'm going to add 2 vertices into it, and that's going to give me this graph here. So, okay, up top, we have my 5 cycle that I created on the first go-around. And now, let's see. I'm going to have 4 vertices there where my triangle used to be. And now this vertex has 1, 2, 3, path of length 3 coming off of it. 1, 2, 3. And so that's isomorphic to H. So this is the idea of subdividing edges. So here we say H is a subdivision of G. Subdivision of G. It's not true that H is equal to the subdivision graph of G, but we do say it's a subdivision of G. So, all right, big theorem. Graph is planar only if it contains no subgraph that is a subdivision of K5 or K33. So that is, if it contains a subdivision of K5 or K33, then it's non-planar. All right, so how do we establish this? Let's assume it has a K5 subdivision in it. So here, I don't know, maybe we have some part of the graph here, some stuff going on, and maybe if we expand this part of the graph, maybe we see here that we have, all right, yeah, maybe we see here that we have a subdivision of K5. So maybe that looks something like, I'll add another vertex in, and maybe I have something like, maybe these edges are, sorry, let me back up a second. Let's not do those ones. Let's say it's, yeah, here we go. Boop, 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 boop. So this, as you can see, is a subdivision of K5. I've subdivided this edge twice, and this edge in K5. Right, so the idea is since K5 is non-planar, a subdivision of K5 will also be non-planar. And this should sort of make sense that just subdividing edges is not going to make a graph planar. If there was a crossing to begin with, just subdividing edges won't make those crossings go away, right? I'll still have crossings even after subdividing. And same idea with K33. So right, I don't know, here's K33, which I know to be non-planar. And if I just subdivide edges in K33, so if I add vertices in here, well, this isn't going to change whether or not it's planar. It's still going to be non-planar. And so if I find this somewhere in my graph, right, a subgraph of my graph, then necessarily I have some subgraph that's non-planar. And so the original graph G is non-planar. Right, so that's the idea. Graph is planar only if it doesn't contain subdivision of K5 or a subdivision of K33. So the one thing that has to be shown now is that if a graph is non-planar, then it has to have a subgraph that's subdivision of K5 or a subgraph that's a subdivision of K33. Now that takes a while. This is perhaps the longest proof we've encountered in the book so far. I'm not going to go through it. I think it's a little bit outside of the scope of our class to fully understand this. I mean, I think it's a good thing to try and make it through this proof on your own, read through it, but it's okay if you don't. What I want you to really get from this is just this test for a graph being planar or not. And so that proof, again, not going to go through it, but that theorem is called Kurowskis Theorem. So a graph is planar if and only if it contains no subgraph that is a subdivision of K5 or K33. And so this is our test to see if a graph is planar, is we look at the graph and we see if we can find a K5 or K33 subdivision somewhere in the graph. Now this is still a little bit difficult to do, right? This still requires some creativity to be able to find this, but it's powerful in that it's a characterization. So if, for example, I wrote a computer algorithm or something like this that takes a graph and looks for subdivisions of K5 or subdivisions of K33, then I would have an algorithm for determining if my graph is planar or not. So that's pretty powerful, even though sometimes it's difficult to do in practice. Now, okay, so let's return to this idea of showing the Peterson graph is not planar. Well, so normally we draw the Peterson graph like this. I think every time in this class where I've drawn the Peterson graph, and maybe I've done a disservice to you by not showing you other representations, or rather other drawings of the planar of the Peterson graph. Right? We usually draw it like this, but another way to draw it is as follows. So what we have for the Peterson graph, again, every vertex is degree 3. Instead, we can draw it with a big outside 6 cycle, like this, with the central vertex here. There's so much wonderful symmetry in the Peterson graph. It's truly a beautiful graph. And remember, the Peterson graph has its circumference is 9, and so we can find there's another way to draw the Peterson graph where you have a big outside 9 cycle and then a central vertex adjacent to some vertices. So let's see here, 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 here. And here are these 5 cycles that we can find in the Peterson graph a lot. And then the central vertex is adjacent to these 3. So I want to show that somewhere in here is a subdivision of either K5 or K33. Well, what I'm going to do, and I think I'm just going to do this by actually deleting these, by actually deleting some edges here. I'm going to, I just need to find a subgraph, so that means I can delete vertices, I can delete edges, and then look for subdivisions. I'm going to delete this central vertex. So here we have this graph, and now I claim that this is a subdivision of K33. So let's look for a subdivision of K33. So one thing to note here is that, and this was pointed out by a student in class, this was very helpful, that these vertices here are each degree 2. So these represent the subdivided edges. So these are my subdivided edges. And so that means this vertex was an original vertex. I'm going to actually use colors here. I'll use blue. Right, I want to identify my partite sets. So blue, it's not adjacent to this one or this one. So those are my 2 partite sets. And then I'll use, how about red here? So these 2 are not adjacent, and they're not adjacent to this one. So these are my my partite sets. And notice here I have, right, every blue vertex is adjacent to every red vertex, except in this case, right here, and here, and here, except these are subdivided edges. So if we remove those subdivisions, what we end up with is K33, right? So removing those gives us the following graph. Sorry, I didn't make this big enough. So we would still have this outside 6 cycle. We're not removing any of those. Those weren't subdivided. But now these 2 vertices are adjacent. These 2 are adjacent after removing the subdivisions, and these 2 are adjacent after removing the subdivisions. And that is another way to draw K33. So the Peterson graph, while you might have thought at the beginning, I don't know, at least I thought this one first looking at the Peterson, is we'd be able to find a subdivision of K5 in it, because, I don't know, it kind of looks K5-ish. What it turns out is we actually have the subdivision of K33 in here. So this is remove subdivisions. And our conclusion now, so Peterson is non-planar by Kurowskis Theorem. So this is kind of cool. So this idea of removing subdivisions, this is going to give us another characterization for planar graphs, which is perhaps easier to put into application. It's a little bit easier to see when a graph is planar or not. So for this, we need to talk about minors of graphs. So graph H is called the minor of a graph G. If H is obtained from G by a succession of edge deletions, vertex deletions, so this is essentially subgraph properties, and then the third new one is an edge contraction. So we haven't talked about edge contractions before, so let me talk about that. for a second, edge contractions. Let's look at an example. So I'll start with this graph here. So here's this graph here. And what an edge contraction is if I take any edge and I identify the two incident vertices with each other. So what I mean by that, here I'm going to isolate this edge here. And I'm basically going to take the two vertices and move them on top of each other. I'm going to keep each of the adjacencies between the two vertices. I'm going to keep those, so the vertices adjacent to this one are still going to be adjacent now to this new one. So I'm like combining the two vertices into one. And so that effect is kind of like I'm smushing this vertex down. I'm like moving this vertex along the edge and identifying it with this one. Some way I'm sort of plopping them on top of each other. So that means this new vertex here will still be adjacent to what it was initially adjacent to, these two. And it'll be adjacent to what this one was adjacent to. So also these two. They actually have the same neighborhood. So we see those, and then the rest of the graph remains unchanged. And so I end up with this graph. I'm going to do another edge contraction just to try and illustrate this a little bit more. I'm going to contract those two edges together. And imagine what will happen when I take those two edges and just slide them together on that edge. So I remove the edge and I take the two vertices and take them into one. So not only do we lose an edge, but we also lose a vertex in this. So I'll still have these two. And now this vertex, so here's going to be my new vertex. That's the result of identifying those two together. This one was adjacent to this one. So I get an edge there. And this one was adjacent to this one. So I have an edge there. And that's all of their adjacencies combined. I still have this edge here, and so I have a triangle. Lastly, one thing I could do, I don't know, just to kind of try and make a point, I could I could contract that edge, and what I'll end up with is a triangle. And so we just obtained the triangle by a succession of edge contractions. And so K3, I'll call this original graph G, K3 is a minor of G. I mean, in fact, it's a subgraph of G, but it's also a minor of G in this way. This is the idea of a graph minor. We can also, right, just being a subgraph, you're also a minor of a graph. You can remove vertices, you can remove edges, but you can also do this new sort of operation on the vertex and edge set of contracting edges. So this gives us one more characterization of planar graphs, and that is neither K5 nor K33 is a minor of G. I guess one thing I should note is that if a graph, if you have K5 or K33 as a subdivision, then this idea of contracting edges, right? If I had a subdivision somewhere, like maybe think of this like a subdivided edge, contracting one of those two edges will produce the original graph. This is a way of removing. So you can think of this like a generalization of removing subdivisions is the same as these edge contractions. And so we get Wagners theorem here. And in my opinion, this is a little bit easier to use than Kurowskis theorem. So one way I'll demonstrate this is with the Peterson graph. So I'll draw how we normally draw the Peterson graph. Except I'm going to draw it a little bit messier for no apparent reason. Here we go. Getting the spokes in, getting the cycles in, like this. And now I'm going to contract edges. So I want to find a K5 minor of this graph. I can do this just by contracting edges. So I'm going to contract this one, this one, this one, this one, and this one. And I'm going to contract all those edges, and now look at what happens when I identify each pair with each other. What I'll get, I'll have 5 vertices left. And let's see, so I'll still have this outside cycle. And now this vertex is adjacent to those two this one and this one, which are contracted together, identified into this one and this one. So this is adjacent to those two. Similarly, this one is adjacent to these two. This one is adjacent to these two. And what do you know? I have K5. So we would say K5 is a minor of the Peterson graph. And then by Wagners theorem, Peterson graph is non-planar. All right, that's it for this video. Thanks for watching, and I'll see you next week.